Hello everyone, and welcome to the Design Day video for Team 21062, the Laser Communications Fine Tracker sponsored by Geost.
I'm Nick Brar.
I'm Patrick Eschenfelder.
I'm Clay Kingsley.
I'm Susanna Marr.
I'm Emily Rodriguez.
I'm Mary Jane Yaziamberger. Communications between low Earth orbiting satellites are critical for a wide variety of applications, ranging from military reconnaissance to basic internet access in rural areas. While traditional methods of communication, such as ultra-high frequency radio communications, are effective, they are between 10 and 100 times slower than laser communications. However, atmospheric effects induce error in the laser signal, making the signal prone to data loss. The Laser Communications Fine Tracker greatly reduces this error, allowing for up to 90% of the beam power to be retained. By reducing this error, significantly more data can be transferred in less time than previous systems.
The system must be able to generate an error signal at 10 Hz with an RMS of 1 arcsecond, and a second error signal at 2 Hz with an angular range of 5 arcseconds. The laser tracker must be able to correct these errors, and in doing so, maintain 90% of the achievable power entering the optical fiber. The system must also have a user-friendly GUI and overall be a contained, professional system.
Tracing the beam through the system, we begin at the laser diode, which emits coherent light at the required wavelength of 1550 nanometers. After this, the beam hits a collimating A-sphere. Next in the beam path is a Keplerian beam expander. In this setup, the F number of the light exiting the error emulator is a function of the beam diameter instead of the lens diameter, so the beam expander ensures the correct F number exiting the system. Following the beam expander, collimated light hits the error emulator mirror, which induces the error in the system using its piezo-driven mount. Next, the beam hits the f6.8 lens. This lens represents the f6.8 half-meter telescope, except with the focal length decrease. In order to replicate the error with a shorter focal length, the error emulator mirror must induce a greater angular error than it would for the half-meter telescope. After passing through this lens, the beam exits the error emulator subsystem and enters the laser tracker subsystem. The first element in the laser tracker is a lens to collimate the diverging light coming out of the error emulator. Next is a fast steering mirror which corrects the error in the system. Following the mirror is a beam splitter sending one beam through a lens into the fiber and the other beam through a lens onto the quad cell. The mirror is a part of a closed-loop system including the quad cell detector. The closed loop is designed to control the fast steering mirror to point the beam to the center of the quad cell detector. With the system aligned such that the center of the fiber and the center of the quad cell are overlapping, the fast steering mirror points the beam into the fiber.
The Laser Communications Fine Tracker consists of two subsystems, the error emulator and laser fine tracking systems. Starting with the error emulator, we see the laser system, which is housed in a cage to aid with alignment. The beam from the laser is then passed through a collimating lens to collimate the light, which keeps the beam from diverging as it passes through the system. The beam then reaches the error emulator mirror, which imparts angular deviation to the beam path. This simulates the effects that would be experienced due to atmospheric conditions on the path from a satellite to a ground receiver, as well as the mechanical variations imparted by the telescope that is intercepting the beam. Moving into the laser fine tracking system, the beam encounters a fast steering mirror, which is responsible for stabilizing the beam, thereby correcting the error imparted on the system. For this part of the demonstration, beam steering is disabled in order to help visualize how the error is impacting the beam's trajectory. After the beam reaches the fast steering mirror, it is passed through a beam splitter, which directs 30% of the light to a quad cell detector located behind the beam splitter and 70% of the light to an optical fiber located right of the beam splitter. As we can see, with beam steering disabled, the beam is unstable and does not produce any meaningful power to the optical fiber. This result can also be seen on the quad cell, as there is a direct correlation of beam deviation for both the quad cell detector and optical fiber. With beam steering enabled, the fast steering mirror is capable of reducing the error significantly and directs the beam onto the optical fiber, which is 10 microns in diameter, with minimal error, resulting in a greater than 90% power retention.
Here is real demo footage of the error emulator mirror. The noise that you hear is the sound of the mirror rapidly generating error by moving in both the X and Y direction. We would now like to demonstrate the error emulator and laser tracker GUIs that we created for the project. Using features such as the calibration tool, status indicators for the system, and real-time data visualizers, we were able to control both subsystems and meet all of our project requirements. With this, I would also like to note that all the tests outlined in our ATP document have been completed, and all of our requirements have been met, such as we were able to generate error that simulates real-life atmospheric and telescopic error. We were able to create a fine laser tracker system that is able to track the laser beam while error is being induced, and we were able to maintain an average of 90% of power onto the fiber optic cable over a period of 10 minutes. This success of our fine laser tracking optical system has big implications in the growing world of laser communications.
1 week after Design Day, we'll submit all of the project deliverables to our sponsor, GEOS. That will include the finalized project, including both subsystems and all associated software, a final acceptance review, all GEOS provided materials, a final report, and the Design Day video and poster.
We encountered and overcame many challenges through the course of this project. Initially, we had selected both of our mirrors from Thor Labs, but eventually needed to switch to mirrors provided by different vendors due to long lead times and the component specifications not being sufficient. Despite the delay in our project timeline, we were still able to overcome and deliver a successful project on time. To compensate for the setback, our team worked on the project 4 to 6 days a week for 3 to 5 hours each day. What proved to be one of the most challenging obstacles was the control loop. Our team learned to successfully implement controls theory with no prior experience. Our team also had little experience with LabVIEW at the start of this project. We learned how to build a complex program that interacts with real instrumentation. We also learned that professors at the U of A are happy to help with any questions or confusions we have with our project. Some of our team members received valuable assistance this way.
The main safety concern for this project surrounded the laser diode that we used. To mitigate this concern, early in the design process, we intentionally selected laser diodes that were low in power. Even with this selection of low-power laser diodes, we took steps to ensure laser safety, such as wearing protective goggles while aligning the system with the visible laser diode, and placing shielding around the beam so that the laser did not reflect off any unseen surfaces away from the optical bench.
Last but not least, we would like to take the time to acknowledge and thank many of the people that helped us and this project succeed over the past year. We would like to say a special thank you to all of GEOS, Dr. Anthony Gleckler, Lisa Bennett, Gary Redford, Darren Williams, Don Henderson, Dr. Eniko Enikov, and so many others for their guidance and support throughout this incredible real-life engineering experience. Our project is a part of a real professional proposal and is just the beginning of laser satellite communications. Along with GEOS, many others are already starting to look into using laser communications to better data transmission through space and on the ground. Laser communications are the future, and this is just the beginning.